Alright, so the main reason I wanted to discuss the ACF and the PACF was because in time series analysis courses, instructors often talk about how to use the ACF and the PACF as if you're following a set of arbitrary rules. But they never go on to show you that these rules actually do what they say they do by comparing the ACF and the PACF to known data. By looking at the ACF and the PACF for known data, we can confirm that those rules actually work. Following them thus becomes natural. It's also important to recognize that these are standard topics in time series analysis, so it wouldn't be right to leave them out. Even so, there are important caveats. The caveats are that, even if you do follow these rules, they might not lead to the best model. Of course, we haven't yet defined what best model actually means, but we will. The real question is, why do all that work when we can get a computer to do it for us? Especially when a computer will do a better job than we can. That is what this lecture is all about. So it turns out that the computers of today are fast enough that you don't need to go through all that work, especially since you might end up with a suboptimal answer. Instead, popular time series packages usually contain a function called ARIMA that automatically finds the best model for you. That is to say, it tries a bunch of different settings and returns the best settings according to some criterion. What these criteria might be will be discussed in the next lecture. In the R language, for example, you can simply call a function called auto.arima and pass in your time series, which is very nice. In stats models, there exists no such function. However, there is a package called PMD-ARIMA, which uses stats models under the hood that does implement the auto-ARIMA function. So basically, we have the power of auto-ARIMA at our fingertips. We just need to install a different library, which luckily still uses stats models under the hood. Now, the PMD-ARIMA API is a little different from stats models, so that would be worth mentioning briefly. Assuming that we have our data as a series, the first step will be to call the auto-ARIMA function. This allows us to pass in an argument called seasonal, as well as the seasonal period m. We will get to what this means later on, but it's basically a seasonal extension of the vanilla ARIMA we've been discussing so far. This will return to us a model object, from which we can make predictions. Note that this is not a stats model object, so the API is a bit different. When we want to forecast, we call the model.predict function. This takes in two arguments which are relevant to us, which are n periods and return conf int. N periods is the forecast horizon, or the number of time steps to forecast, and return conf int should be set to true if you want the confidence bounds along with your prediction. So that's for the out-of-sample data. For the in-sample data, you want to call the function model.predictInSample. This takes in two arguments, start and end, along with some others which we won't worry about. Technically, you can return confidence intervals for the in-sample predictions as well, although that is less common than for forecasts. Unlike stats models, start and end should be specified as integers, which correspond to the indices of the train set. In stats models, start and end can be integers, but they can also be datetime objects or strings, corresponding to the index of the panda series you passed in for training. In order to better understand what auto-ARIMA is doing, we'll have to discuss seasonal ARIMA. This will be brief since it's not as important to know compared to the vanilla ARIMA. Just understand the basic high-level points and you will be fine. Again, I want to mention that seasonality is not usually observed in stock prices, but stock prices do not comprise all of what can be considered financial data. And so these concepts do show up in financial literature, as they should. One example of this is that the weather, or in other words, actual seasons like summer, winter, and so forth, affect when and where people purchase real estate. So that's one example of where seasonality affects finance. Okay, so seasonal ARIMA, abbreviated as SARIMA, gives us three new hyperparameters called capital P, capital D, and capital Q, which are analogous with the lowercase versions of the ARIMA. So now we have 6 hyperparameters in total. We usually write this as ARIMA PDQ cross capital P, capital D, capital Q, subscript M, where M is the seasonal period. The reason why we add the cross is because it turns out when you write the model using operators, you end up multiplying the non-seasonal parts by the seasonal parts to get your full model. This is outside the scope of this course, since the notation is very messy and doesn't really add any benefit on top of what we are already doing. However, if you want some simple intuition, we can discuss what the seasonal part might look like in isolation. So let's suppose we want to consider only the seasonal part of the seasonal ARIMA. If we have capital D equals 1, that means we difference y of t once using the seasonal period. Our notation for this is delta sub m y of t, which is equal to y of t minus y of t minus m. So this is just like regular differencing, except that regular differencing subtracts from one time step behind, and that measures the slope or the trend. With the seasonal part of seasonal ARIMA, we subtract from one period ago. So if we have monthly data and t is equal to March, then we subtract from the previous March. Note that when we discussed stationarity earlier, we discussed certain characteristics of time series that indicate that it is not stationary. Examples of this were trend and changing variance. If either the level or the variance changes over time, then the series is not stationary. Seasonality is the other key component of this. Stationary time series should also not exhibit seasonality. So if you find a time series that does exhibit seasonality, then you would say it's not stationary. Interestingly, what we found in our previous code examples was that it is possible for a non-seasonal ARIMA to model the airline passengers dataset quite well, even though it has no seasonal component. In fact, it's possible for a purely autoregressive AR2 model to perfectly represent a sine wave. So it's not that ARIMA cannot model seasonality, but including seasonality explicitly by using SARIMA can lead to a better model. So without loss of generality, let's suppose that we have not difference so that we can keep using the variable yt. Or you can pretend yt now represents the new differenced time series, doesn't matter. The seasonal autoregressive part is again what you might expect. Yt is regressed on past data points in the time series at multiples of m away from t. So for example, y of t depends on y of t minus m, y of t minus 2m, and so on. For the moving average part, we again have the same pattern. Y of t depends on past errors at multiples of m, so that would be epsilon at t minus m, epsilon at t minus 2m, and so on. Finally, once we have this seasonal part, we multiply it with the non-seasonal part, and that gives us the full SARIMA model. In code, there is actually one extra component, which gives us the SARIMAX model. The X part is actually pretty nice, and I think it will make you feel like this model can actually be applied to so-called real-world data. The X part refers to exogenous variables. So imagine that you have a time series of length big T. At each point in the time series, you have some feature vector of exogenous data, such as maybe the sentiment of tweets by Elon Musk, or the sentiment from various financial news sites. You can include this in your model by passing in an array of feature vectors of size t by d into the AutoArima function. One caveat to this is that, when you want to make predictions, you have to know what these features are, so you want to consider whether or not this is actually practical for you. In any case, we won't be making use of this, but we will see on our output SARIMAX, so this is just in case you wanted to know what that means. Otherwise, consider this topic outside the scope of this course.